All right. So now that we have an idea of sort of the definition of what sequences are, let's try and do this for some actual examples here. All right. So we're going to do 3 examples here. um, and we want to do each of these 3 things for the given sequences. Right? We want to find the next 2 terms in the sequence. We want to write down a recurrence relation, and then we want to give an explicit formula. So let's say we have this sequence 2, 5, 8, 11, 14, and so on. Right? So let's look at this. What would the next 2 terms of this sequence be? Right? So in order to do this, a good start is to say, well, how am I getting from one term to the next? Right? So, 2 to 5 to 8 to 11 to 14. What are we doing? Right? What are we doing? Well, here we're adding 3. Here we're adding 3. Here we're adding 3. Right? Each time we're adding 3 here. So then hopefully it makes sense if we say, well, let's add 3 again. And this will be 17. And then add 3 again. And this will be 20. So these are the next 2 terms, 17 and 20. Okay? All right. Oops. That's not to do. There we go. So now that we have the next 2 terms, and we've actually done a lot of work to figuring out then what the recurrence relation has to be. So look what happens. We have to keep adding 3 each time, right? So what we're saying then is, like, to get, say, the 4th term, we have to take the 3rd term and add 3. So the pattern there is, well, to get the next term, we have to take the previous term and add 3. Right? This applies for n starting at 1. Right? And then here, if we just add on a1 is 2, there we go. Right? So remember that about a recurrence relation is we have to come up with the formula for how to move from one to the next, but then we also have to specify, well, where do we start at? Because a recurrence relation, it needs a starting value, sort of a seed value, to run its algorithm off of. Right? Okay. So for the 3rd term here, or sorry, the 3rd part, we want an explicit formula. So again, I find the best way to sort of figure out an explicit formula is to write out a chart like this. Right? So when n is 1, what happens? When n is 2, 3, 4, and so on. These are actually a little too close. Okay. So let's look at this. Right? So here, we have our 2, 5, 8, 11, and 14. Right? So, this is where we start. So we're kind of just stuck with this 2. To get from 2 to 5, we add 3. Right? To get from 5 to 8, we add 3 again. So this is like 2 plus 3 plus 3. Or a better way to write this is 2 plus 3 times 2. Right? Because I added 2 copies of 3. Okay? Here, I'm going to add 3 again. So it's going to be 2 plus 3 copies of 3. Okay? Here, we're going to have 2 plus 4 copies of 3. Right? Is that hopefully making sense? So because of this, we can say, well, let's see, is there a pattern here? Well, we see a nice pattern going on here. One of these days I'm going to stop doing that. There's a nice pattern here, right? This is 2 plus 3 times 1 less than the index. 2 plus 3 times 1 less than the index. If that holds up, this should be 2 plus 3 times 1, which it is. And this should be 2 plus 3 times 0, which it is. So that means the explicit formula would be 2 plus 3 times n. Right? And again, this applies for all these n values going forward. Right? So you can even double check that, if I plug in, let's see, n equals 6, I'm going to get 2 plus 18, right? Right. 6. 2 plus 18 is 20. Oh, I did this wrong. It's not 3n, it's 3n minus 1, because it was 3 times 1 less than the index. Sorry about that. There we go. Now let's try that again. If we plug in n equals 6, we get 2 plus 3 times 5, which is 2 plus 15, which is 17, and that was the 6th term in the sequence that we found in part 1. Sorry about that. So again here, this number that we're multiplying the 3 by, this number here, is always 1 less than the index. Right? And since that's the case, then we write that in with an n minus 1. All right, so let's do this again with another example. So let's say we start with 64, then go to negative 32, and then go to 16, and then go to negative 8, and then 4, and negative 2, and so on. Right? So here's the first few terms. Let's see if we can figure out what the next one has to be, or the next 2 terms. Right? So think about, what are we doing in each step here? So 64 minus 32, 16, negative 8, 4, negative 2. What's going on here in each of these steps? Right? Well, what's going on is from here to here, we are divided by negative 2. Right? Here we divided by negative 2. Divide by negative 2, and so on. So, again, it should make sense that for the next 2, I just keep dividing by negative 2. So if I divide negative 2 by negative 2, I get 1. If I divide 1 by negative 2, I get negative 1/2. So these are the next 2. Right? Okay. So there's our next 2 terms. The recurrence relation here is, again, pretty simple. Right? It's pretty simple here. Just like last time, we know we're always dividing by negative 2. So an plus 1 is going to be an over negative 2. Right? There's a few ways you could write that. You could also write an plus 1 equals negative 1/2 an. That's probably the better way to think of it. Instead of dividing by negative 2, think of it as multiplying by negative 1/2. And again, these apply for n starting at 1. So we need to, again, specify that a1 is 64. So I'm going to box these ones here. Right? Again, either formula here is perfectly acceptable. So, pick your favorite one. Right? Now, again, let's look at finding an explicit formula for this. right? An explicit formula here. So again, I'm going to continue drawing this chart because I think it's really quite helpful, at least for me. 1, 2, 3. Let's look at the first 4 here. All right. So looking at our first 4, we have 64 minus 32, 16 minus 8. Okay. So let's look at what we're doing. All right. So here, we're just going to have a 64. Here, I'm going to have 64 over negative 2. Okay. Here, I'm going to have 64 over negative 2 squared, right? Because I divided by the negative 2 twice. Here, I'm going to take this and divide by another negative 2. So we're going to have divided by negative 2 3 times. Okay? And so if you think about it, right, this is 64 over negative 2 to the first power. This one here is 64 over negative 2 to the 0 power. And so an explicit formula here could be 64 over negative 2 to the n minus 1. Right? And that's a perfectly great explicit formula. Right? This works perfectly. Now, this one, I want to show you something because this is actually a little bit useful to know. To be able to rewrite a sequence like this. So on the bottom here, I'm going to separate out the negative sign. Right? So that just allows us to, write it like this, just using some laws of exponents. But now, if I divide by negative 1 or multiply by negative 1, it's the same thing. So I'm going to just put the negative 1 to the n minus 1 out front like this. And write this. Now 64, let's see, that's 2 to the, 1, 2, 3, 4, 5, 6th power. Right, 2, 4, 8, 16, 30, yeah, 6th power, right? So, if you really wanted, what we could do is write this as negative 1 to the n minus 1 times 2, this would be to the 5 minus n. Right? No, sorry, not 5. 7. 7 minus n. Because it's 6 minus this term. Right? So this would be another perfectly acceptable explicit formula right here. Right? So I just want to point out that being able to factor out that negative sign like that is actually quite useful. Right? Okay, I think this video has gone on long enough here. So I think we'll stop here. Right? But hopefully this gives you an idea of sort of how to, do the pattern recognition that goes into finding formula for sequences.